All right, let's fire up a time machine. Well, sort of. Today, we're using a high-fidelity physics engine to put one of history's most feared weapons to the test, the Roman ballista. We're about to find out if ancient engineering really lives up to its incredible, legendary reputation. So here's the big question, right? For centuries, we've all heard the stories of Roman artillery, machines that could supposedly shatter fortress walls and just completely dominate a battlefield. But was this thing a genuine marvel of engineering? Or has the story gotten a little stretched over the last 2,000 years? That is exactly what we are here to find out. First things first, we need to understand the legend we're actually putting to the test. You see, the Roman ballista wasn't just another catapult. No way. It was spoken of with this kind of awe, like it was the absolute peak of ancient military tech. I mean, just listen to those words: devastating force, legendary accuracy. These aren't just filler words. They paint this incredible picture of a weapon so powerful and so precise that it could literally change the outcome of a war. This is the reputation that has echoed through history. But where did the blueprint for such a legend even come from? Well, believe it or not, it comes from ancient texts. We essentially have instruction manuals left behind by the very engineers who designed these incredible machines. And that, right there, is where our real mystery begins. Let me introduce you to the man at the center of all this, Vitruvius. He was a Roman architect and engineer who, about 2,000 years ago, literally wrote the book on how to build a ballista. His famous work, De Architectura, is our main source, giving us incredibly detailed, precise instructions. And this brings us to the absolute heart of the problem. Were Vitruvius's plans like a practical, step-by-step IKEA manual that workshops all over the empire followed to the letter? Or were they more like a modern concept car? You know, an ambitious theoretical design showing what was possible, but maybe not what was actually practical to build over and over again. To find out, we don't need to go out and build one from scratch. Nope. Instead, we're heading to the digital proving ground. We're going to build a digital ghost of the ballista inside a computer, where we can push it to its absolute limits without splintering a single piece of real-world timber. And this really breaks it down, doesn't it? On the one side, you have the theory, Vitruvius's ancient words written down on papyrus. And on the other, you have our test, a super powerful physics engine that can simulate everything, right down to the grain of the wood and the tension on a single strand of rope. So you might be wondering, how in the world do you stress test a 2,000-year-old design? Well, it all comes down to translating those ancient principles into modern computer code. Okay, so the process works in 4 key steps. First, the simulation has to digitize the very heart of the machine, the torsion mechanics. That's all the coiled-up power you get from twisting those huge bundles of rope. Next, it models the timber's elasticity, figuring out exactly how much that wooden frame could bend before, it snapped. Then, a super crucial part, it calibrates the rope tension to mimic what ancient materials could handle. And finally, the best part, we get to fire the virtual ballista thousands and thousands of times to get all the data. So after running thousands of different scenarios, testing every variable you can possibly imagine, from different types of wood to the humidity in the air, the simulation is finally complete. Our digital ghost has been pushed to its absolute limits, and the data is in. And so we come right back to that huge question we started with. Was the Roman ballista an engineering marvel, or was it an exaggerated myth? The verdict is finally here. Let's break down the numbers. The legends claimed a range of over 400 meters. The simulation, it maxed out at about 370 meters. Now, that's a little short of the legend, sure, but just think about that distance. That's a projectile flying clear over 3.5 football fields, end zone to end zone. Projectile speed, almost a perfect match, coming in at 48 meters per second. But here is the most fascinating part, the structural integrity. At maximum tension, the simulation showed the wooden frame was prone to dangerous stress fractures. This tells us something huge. It was an engineering marvel, absolutely, but it was a marvel that operated right on the razor's edge of self-destruction, pushing those ancient materials to their absolute breaking point. So what's the big takeaway here? Well, it's that we can use modern technology to become historical detectives, putting these ancient claims to a real scientific test. But more than that, we've caught a glimpse into the whole Roman engineering philosophy. See, they weren't just building things to last. They were pushing the absolute limits of the materials they had. The ballista wasn't just a powerful weapon. It was a testament to a culture that valued maximum performance, even if it meant living on the edge of catastrophic failure. The legend wasn't so much an exaggeration as it was a celebration of that sheer audacity.
And all this leaves us with one last, really exciting thought. If we can digitally test the physics of a Roman siege engine, what else can we test? The legendary, almost magical burning properties of Greek fire? The supposed acoustic perfection of ancient amphitheaters? What other ancient facts are just out there, waiting for their turn in the digital proving ground?